United 243, descend and maintain flight level 240.
United 224, descend and maintain 11,000.
United 430, descend and maintain flight level 240.
Sundance 463, radar service is terminated. Squawk 1200, frequency change approved. Good day.
United 435, do not exceed 290 knots for
The pilot of an air carrier inbound to Lindbergh was issued traffic. The pilot reported traffic in sight. Unfortunately, the pilot had the wrong aircraft in sight, subsequently resulting in a mid-air collision. A VFR pilot unfamiliar with the area was operating in the terminal control area without a clearance and collided with an air carrier.
I had an aircraft that was at flight level 280, straight and level. There was an aircraft directly above that aircraft at flight level 350 requesting lower. So I descended the aircraft to flight level 290. The aircraft that was at flight level 280 told me that he was responding to a resolution advisory and was descending. The aircraft descended. I observed the aircraft above him was straight and level at flight level 290. I asked the aircraft what his altitude was. He verified that he was at flight level 290. I relayed this to the aircraft that was responding to the RA, and he said, well, regardless, I have to respond to the RA. It caused a little bit of problems with me because he descended into somebody else's airspace. I had to do a lot of hurry-up coordination. And later, the pilot of the aircraft called the facility and explained. He said he knew that he was causing a problem, but he had to respond to the RA. And even though I told him that the traffic was no factor and the traffic was straight and level above him, he had no choice but to respond to the RA. It turned out there was not a loss of separation, but there was a scramble there. It made a situation that was normal and routine a scrambling situation for me. I had to move the aircraft out of the way for this aircraft that was responding. It disrupted my flow, the way I was working, and it was a disturbance. It was a disruption.
You're concerned about how TCAS affects your ability to control traffic. That's understandable. No one wants more complications. But TCAS is here because through technology, we can finally address long unmet needs. Needs which have been the focus of aviation industry research and development for more than 30 years. And this program is about how you can work with TCAS to increase safety. Technological innovation has made possible the development of a family of devices that provide airborne traffic alert and collision avoidance information. Traffic alert and collision avoidance systems interrogate transponders of nearby aircraft, analyzing position, bearing, and altitude, and alert the pilot to the presence of potential conflicts. TCAS-1 is a proximity warning system. It provides the pilot with traffic advisories, TAs, informing them when transponder-equipped aircraft are potential threats. TCAS-2 expands this capability by providing guidance for vertical avoidance maneuvers called resolution advisories, RAs. And new generations of software and hardware currently under development will refine the current systems and provide enhanced capabilities. That's what TCAS is. It's also important for you to know what TCAS is not. TCAS is not an air traffic control system. However, it is a system that directly affects air traffic controllers and the ATC system, as do other systems, such as Conflict Alert and MCI Alert.
Yeah, I think there's concern in the controller group that pilots are trying to take over the function of controlling the overall traffic flow with TCAS. And that's not really the case. We're not really interested in actively being involved in assessing traffic at all times. I mean, we'd rather be able to operate the airplane and pay attention to whether the airplane is operating as it should and is in compliance with the clearances that we've been given, and that we're operating it in an optimum way. There's enough there in workload that we really can't absorb a whole lot of activity where we're heads down looking at a small display trying to make heads or tails out of all the different airplanes and where they're headed.
But TCAS can also affect you and your traffic plan. Aircraft responding to RAs may leave their assigned altitudes. So you need to know about TCAS, how it works, and in which traffic situations TCAS events most often occur. TCAS interrogates aircraft transponders in the surrounding area once a second to a range of about 14 miles. The return from each intruder aircraft is analyzed to determine its relative range, bearing, altitude, and vertical speed. The 1-second sweep rate allows TCAS to track and resolve fast-developing traffic conflicts. Using intruder aircraft track data and closure rates, TCAS projects the path for each aircraft to determine the time to the closest point of approach, or CPA. In this case, there is one threat, the climbing intruder. When the intruder is 40 to 45 seconds to the CPA, TCAS issues a traffic advisory, TA. Note that it is 40 to 45 seconds, not 5 to 10 miles. TCAS calculates CPA based on time, not distance, and the time to CPA is based on closure rates.
Traffic, traffic.
An audio enunciation calls the pilot's attention to the TCAS display. The display provides the pilot with an approximate relative position of the intruder. The crew then tries to visually acquire the intruder. When the intruder is 25 to 30 seconds to the CPA, TCAS issues a resolution advisory.
Climb, climb, climb.
The resolution advisory, or RA, suggests a vertical avoidance maneuver. In this case, a 1,500 foot per minute climb.
No pilot wants to deviate from the air traffic clearance that he's on. Pilots are very comfortable with the guidance they have from controllers, and they don't want to just arbitrarily leave a clearance. Although if you ask a pilot with a radio call after he's deviated off a clearance for a TCAS resolution advisory, are you required to follow that advisory? I'd say 9 times out of 10, the pilot's going to tell you my company requires me to follow that advisory, when in fact there's probably a little bit more latitude if you got right into the textbook and looked at the words that are written.
For example, when the aircraft is on approach to an airport with closely spaced parallel runways, or when the crew has definitive visual acquisition of intruder aircraft, the pilot may choose to ignore the RA. But since there is no guarantee that aircraft in sight is the intruder, pilots are trained to follow the RA when any doubt exists.
Climb, climb, climb.
Pilots understand that responses to RAs are not emergency maneuvers and do not require excessive control inputs, but sometimes they are not executed perfectly. As soon as possible after the RA, pilots should inform ATC of the RA. Now let's look at some of the factors which can cause TAs and RAs. If the intruder has operating mode C, TCAS determines altitude and tracks any change in altitude to determine the intruder's rate of climb or descent. TCAS then analyzes all of this information and projects aircraft paths, identifies potential threats, and determines the time to the closest point of approach. The TCAS separation minimums, called ALIM, vary by altitude and are less than ATC separation minimums. If the intruder is projected to penetrate TCAS separation minimums at the closest point of approach, an RA is issued. Controllers should remember a few important points. First, TCAS analysis is based on speed and time, not distance. So faster-moving aircraft will be classified as threats at a much greater distance than slower-moving aircraft. Second, TCAS determines altitude from the Mode C readout of the intruder aircraft, so their Mode C must be accurate for TCAS to accurately identify conflicts. Also remember that TCAS determines only the rate of climb and descent and cannot determine when the intruder aircraft will level off at assigned altitude. For example, TCAS projects the path of this climbing intruder aircraft and identifies it as a conflict because TCAS does not know the intruder aircraft's clearance will have it level off below the TCAS aircraft. Analysis of hundreds of TCAS events has led to the identification of several common TCAS conflict situations. Recognizing when these situations can occur will help you anticipate when TCAS advisories can occur, so you can plan ahead. Each of these event types will be described in greater detail in the second part of this program. The most basic TCAS event occurs when two aircraft flying near the same altitude have paths that TCAS determines can lead to a conflict. This can also happen when TCAS analyzes the paths of multiple level-flying aircraft and identifies a potential conflict. These level flight conflicts typically occur with closely spaced parallel approaches or with VFR aircraft passing less than 400 feet above or below the TCAS aircraft. Vertical movements in the vicinity of TCAS-equipped aircraft can result in several types of conflicts. For example, the TCAS-equipped aircraft can be climbing or descending toward the intruder aircraft. The intruder can be climbing or descending toward the path of the TCAS aircraft. Or two TCAS aircraft can be converging. In this last case, the TCAS systems coordinate their RAs through their Mode S transponders. So when two TCAS-equipped aircraft enter into a conflict, each aircraft is issued a complementary RA, a coordinated encounter. Each of these conflicts can result in resolution advisories that interfere with your traffic plan. For example, in altitude crossing RAs, the descending aircraft may be told to increase altitude, leveling it off above the climbing aircraft. Or a climbing aircraft may be told to increase climb towards the descending aircraft. TCAS doesn't know aircraft intent, where the climbing or descending aircraft will level off. It only knows the factors which lead to a projected CPA, range, bearing, and closure rate, and how to keep the aircraft apart.
Pilot reaction to a crossing RA, if he has, I would say, from a human factor standpoint, if he has any information on what that other airplane is doing, be it from air traffic or from visual acquisition, that he's going to probably try to find a way not to cross through the other airplane's altitude and resolve it either through a turn, or if he can still has a chance to intervene with a reduction in vertical rate, be it climb or descent, he's going to do that if he can. If the alert occurs, if a crossing RA occurs, and he has no other information prior to getting it, and he's just, there it is, I've got it, he's going to go with the RA.
Understanding how TCAS works in each of these types of situations will help you to anticipate and manage TCAS events. Let's look at some of the factors that can affect the likelihood of TCAS events. Note which aircraft under your control are TCAS equipped. The flight strip will tell you. Knowing this will also help you anticipate coordinated encounters. The horizontal and vertical speed of the TCAS and intruder aircraft affect how far TCAS projects flight paths and the TCAS conflict area. Note whether aircraft are squawking Mode C. Non-Mode C aircraft will generate TAs only, and Mode C aircraft must be accurately transmitting altitude information. Otherwise, you may get erroneous RAs. Pilot skill is another factor. Less experienced pilots transitioning your area may deviate from their altitude and conflict with the TCAS aircraft. And finally, look at your airspace and control techniques with TCAS in mind. You should be able to identify where and when potential TCAS conflicts may occur. Common arrival and departure points, parallel runways, standard turns or vertical maneuvers, or any other procedures that may trigger TCAS conflicts can be identified. For example, when climbing departures towards inbound traffic, keep in mind that excessive rates of climb can set off an RA. Remember that you can reduce the potential for conflicts.
If the pilot has time to communicate to you and he is following his resolution advisory, then you pretty much have to let him do what he's going to do, and when possible call the traffic to him or any other traffic around him if he's deviating from his assigned altitude.
I've found myself calling a lot more traffic and being a lot more specific, as opposed to just saying where the traffic was, trying to give them more information to preclude them from going into a TCAS situation. I am very aware of aircraft that are TCAS equipped. When I see that in their flight plan, I always try to call traffic to any aircraft that are in their immediate vicinity, because I'm very wary that they might get a resolution advisor, especially in a climbing and descending mode. If there's an aircraft that's climbing to an altitude or descending to an altitude that's near theirs in their immediate vicinity, I make the TCAS equipped aircraft very much aware of that.
Northern 273, say altitude.
Northern 273, descending for TCAS.
Northern 273, roger. Traffic 2 o'clock, 2 miles northbound, Cessna, level at 7,000. Northern 273's TCAS descending into your airspace.
November 31 Romeo, traffic alert, traffic 10 o'clock, 3 miles eastbound, a Boeing 727, descending out of 8,000.
Even when TCAS events are handled properly, they can be disruptive.
Northern 273, traffic no factor. We're going to need a report on that deviation after you land, Captain.
All right, Northern 273, we'll call you when we get on the ground.
Forms, uncertainty, discomfort, more work. Not exactly what we want, is it? Sure, controllers and pilots are given immunity for TCAS-induced deviations or separation errors, but that's not what we really want to happen. We want the system to work, for all of us. Pilots know that following an RA may result in a deviation from their clearance, so they're trained to inform you of the RA as soon as possible. But remember, their first priority is to fly the aircraft. Once informed, you should not knowingly issue clearances or control instructions that are contrary to the RA. Continue to provide traffic advisories and safety alerts for the subject aircraft and all other aircraft under your control as appropriate. Also, don't assume that other aircraft in proximity to the subject aircraft are involved in the RA or are aware of the subject aircraft's intended maneuvers. Again, continue to provide those aircraft with control instructions, safety alerts, and traffic advisories. Once the event is over, report the TCAS event on the TCAS event questionnaire. The report is voluntary, but we strongly suggest that you fill one out. These event reports are essential to improving the system. Controller input has already led to system modifications, which have helped both pilots and controllers. Now let's take it to the next level. How can you decrease the likelihood of RAs? Obviously, it takes a team effort, and the FAA and the aviation industry are working on the technology and pilot sides. But what can you do to make your life easier? Take TCAS into account when developing your traffic plan. This means understanding TCAS system operations through this tape and other information available through your facility. Note TCAS-equipped aircraft under your control. It is part of the Flight Strip Aircraft Equipment Identifier, and it helps increase your awareness. Understand and anticipate aircraft movements that may induce TCAS TAs and RAs. Think about the general types described in this videotape in relation to your specific airspace. Utilize air traffic control techniques that will minimize the potential for RAs. Again, think about your airspace. And finally, continue to provide traffic advisories and safety alerts to aircraft responding to a TCAS RA. Remember, pilots deviating for TCAS should return to their original flight paths once clear of the conflict. In most circumstances, you should not have to issue additional control instructions. Of course, all these are easier said than done, and the details will vary with your facility's airspace and traffic patterns. But getting things moving facility-wide will make the system work more smoothly for everyone. The following scenarios demonstrate typical TCAS-2 responses to common en route traffic conflicts with Mode C equipped intruder aircraft. They are based on studies of hundreds of TCAS events. As you watch each scenario, think how it may apply to your airspace or to situations you may have recently encountered, and how your traffic plan could be affected. Stop the tape after each scenario and discuss the circumstances that may apply to your facility. Then coordinate all ideas through your appropriate facility channels. The white aircraft is TCAS equipped IFR level at 10,000, and the red aircraft is non-TCAS VFR leveled at 9,500, but unable to hold at altitude due to turbulence or pilot error, deviating up to 9,700. TCAS will issue a climb RA to maintain vertical separation with the VFR traffic. Multiple IFR aircraft are holding over an intersection, leveled at 7, 8, and 9,000, heading in the same direction. A VFR intruder transitioning the area at 8,500, unable to hold altitude due to turbulence or pilot error, is deviating as low as 8,300. The TCAS in the aircraft at 8,000 feet issues a descend RA. When the TCAS aircraft descends, it loses separation with the IFR aircraft at 7,000. TCAS then issues a climb RA to increase separation with that traffic. We now add a new IFR aircraft to the previous scenario. This aircraft is descending at 2,000 feet per minute to enter the holding pattern at 10,000. The TCAS on the aircraft at 9,000 issues a descend RA, creating a conflict with the aircraft at 8,000. The TCAS then issues a climb RA to return the subject aircraft back to 9,000. The red TCAS aircraft is level at flight level 240. The white aircraft is descending from flight level 280 to flight level 250 at 3,000 feet per minute. TCAS interpretation of this conflict will vary according to the positions of the aircraft. TCAS will either issue a climb RA to allow the intruder to pass under the TCAS aircraft, or a descend RA will be issued. Now both aircraft have vertical rate and both are TCAS equipped. The white TCAS aircraft is descending from flight level 260 to flight level 240 at 3,000 feet per minute, while the red TCAS aircraft is climbing from flight level 210 to flight level 230 at 3,000 feet per minute. As in the last scenario, TCAS interpretation of this conflict will vary according to the positions of the aircraft. Aircraft may be issued coordinated RAs to reduce their climb and descent. This will result in the aircraft leveling off prior to their assigned altitude. Or the aircraft will be issued coordinated RAs to increase the rate of climb or descent, which will result in each aircraft passing through the intruder's altitude. TCAS will analyze the situation and attempt to choose the RAs that will cause the minimum disruption to each aircraft's flight path.